Have you ever wondered why we can't reach absolute zero, the point where all thermal motion stops? It's a question that has puzzled scientists for centuries, and the answer is both fascinating and frustratingly complex. But here's the kicker. Despite our best efforts, absolute zero remains an impossible dream, and this is the part most people miss, why it's fundamentally unattainable. While most of the world uses Celsius and the United States sticks to Fahrenheit, scientists often prefer the Kelvin scale. Unlike Celsius or Fahrenheit, Kelvin starts at absolute zero, the theoretical point where all molecular motion ceases. 0 Kelvin, 0 K, is equivalent to negative 273.15 degrees Celsius, a number that might seem arbitrary but is deeply rooted in the laws of physics. Yet no natural or artificial system in the universe has ever reached 0 Kelvin, and it's unlikely any ever will, though we've come astonishingly close, achieving temperatures as low as 0.000004 Kelvin. So what's stopping us? Temperature, at its core, measures the average kinetic energy of particles in a substance. As energy increases, particles move faster, and temperature rises. Conversely, as energy is removed, motion slows. Logically, you'd think that if we keep extracting energy, we eventually reach a point where all motion stops, absolute zero. But here's where it gets controversial. The third law of thermodynamics tells us this is impossible, and it's not just a matter of better technology. The third law, often overshadowed by its more famous siblings, states that reaching absolute zero would require an infinite number of steps to remove all thermal energy from a system. Walther Nernst, who formulated this law, put it succinctly: it's impossible to reach 0 Kelvin in a finite number of steps. Experiments have repeatedly confirmed this. No matter how much heat we remove, there's always a tiny bit left, keeping temperatures just above absolute zero. Statistical mechanics further proves this isn't a limitation of our methods, but a fundamental truth of the universe. And it gets even more mind-bending. Scientists have shown that reaching absolute zero would also require an infinite amount of time, meaning it would take an infinitely old universe for 0 Kelvin to exist. Is this a flaw in our understanding of physics, or is absolute zero truly unattainable? Let's discuss in the comments. So how do we get so close? Techniques like refrigeration cycles, which move heat from one place to another, can cool substances to just a few degrees above absolute zero. For example, liquid helium can reach negative 269 degrees Celsius, 4 Kelvin, and using helium-3 and even rare isotope, we can go slightly colder. For extreme cold, methods like nuclear demagnetization and laser cooling come into play. Laser cooling, which earned the 1997 Nobel Prize in Physics, uses lasers to slow atomic motion, bringing microscopic samples to within a billionth of a degree of absolute zero. Even more exotic techniques like matter wave lenses have cooled atoms to temperatures 10 times lower, but absolute zero remains out of reach, and this is the part most people miss. While physicists sometimes talk about negative temperatures, these aren't colder than absolute zero. In fact, they're hotter. Negative temperatures occur in systems with a maximum energy limit, where adding more energy reduces entropy. These systems release heat when exposed to normal environments, making them far from cold. So, the next time you hear about negative temperatures, remember, it's not about being colder than cold, but about the strange ways energy behaves under extreme conditions. Absolute zero remains a tantalizing frontier, a reminder of the limits of our universe and the elegance of thermodynamics. But is it truly impossible, or just a challenge waiting for a revolutionary breakthrough? What do you think? Share your thoughts below. Let's spark a debate.